Insulin is, and I think Richard DeMarchi made this observation first, is a miraculous substance and a very imperfect drug. Nature evolved it to be secreted by the pancreas in response to all kinds of metabolic signals and be part of that metabolic control, not to be put into a vial or a pen and shaken up and stirred and injected into an arm, although it's a life-saving therapy.
As you just heard from Dr. Baker, natural insulin was not designed as a therapeutic, but small changes to its structure can improve its suitability as a treatment. Let's learn about some of those changes now. Insulin is a hormone that regulates physiological glucose levels in the blood. A diabetic patient is unable to control those levels because her pancreas doesn't adequately produce insulin. Over time, this lack of control can lead to blindness, nerve damage, and kidney disease. While insulin isolated from bovine and porcine pancreas was used to treat diabetes for over 50 years, it didn't have the same amino acid sequence as human insulin. But in 1982, Eli Lilly and Genentech used recombinant DNA technology and bacteria to manufacture insulin with the same primary sequence as human insulin. This was the first time that genetic engineering and fermentation were brought together to produce a biologic drug. But this insulin took longer to become active and lowered blood glucose for a prolonged period of time compared with endogenous insulin. Let's take a look at why. Insulin can exist as a monomer, a dimer, or a hexamer under different conditions. In the pancreas, it's stored as a hexamer complexed with 2 zinc ions. But it only interacts with its receptor as a monomer. The recombinant insulin formulated for injection includes zinc ions, so it exists as a hexamer. These hexamers must first dissociate into monomers to be absorbed into the body. But insulin delivered in this manner has a propensity to form dimers. This delays the onset of its action and clearance from the body. But why does insulin form dimers? The key interactions stabilizing the dimer are between the C-terminal ends of each monomer's B chain. First, the dimer is stabilized by hydrophobic interactions and surface complementarity between the proline at B28 and the loop at B20 to B23 of the partnering monomer. Surface complementarity is when surfaces of 2 proteins fit together like 2 pieces of a puzzle. Second, the dimer is stabilized by the formation of 4 hydrogen bonds that are part of an anti-parallel beta sheet between residues at the C-terminal end of each monomer. A healthy pancreas rapidly secretes a bolus of insulin at mealtime, as well as continuously secreting low or basal levels of insulin throughout the day. Ideally, recombinant insulin therapies should have the same therapeutic profile as a healthy pancreas. Toward this end, scientists began to look for insulin analogs where dimerization was unfavorable as a way to provide diabetics with a more rapid-acting and rapid-clearing insulin. By studying proteins with homology to insulin, an important analog with improved performance was found. Recombinant insulin-like growth factor, IGF-1, was also being studied at Lilly. It is structurally similar to insulin, but with a much lower tendency to dimerize. At the C-terminal end of this molecule, the amino acid sequence at B28 and B29 is lys-pro. In insulin, the sequence at B28 and B29 is pro-lys. Chemists hypothesized that switching the sequence in insulin to lys-pro could generate an analog with reduced dimerization. This analog became known as insulin lispro. Let's listen to Jeff Baker talk about studies that led to the discovery of insulin lispro.
Bruce Frank and I were having a meeting with some European regulators, and one of the European regulators said, well, how many insulin analogs did you have to screen before you came up with this one? And Bruce and I kind of looked at each other, desperately trying to telepath one to another what we were going to say, and we kind of smiled and we said, well, this was not a product of high-throughput screening. This was designed. This was looking at the structure of insulin, the structure of related molecules such as IGF, and understanding the biochemistry and saying, if we make these changes, the following outcomes are very, very likely to occur. And then, in fact, those outcomes will be clinically relevant in this way. and it turned out to be right, which was very satisfying.
Insulin Lispro is as effective as insulin in maintaining blood glucose levels in vivo and has a faster onset of action. This graph compares the blood glucose levels of type 1 diabetics after injection of recombinant human insulin or insulin Lispro immediately before a high-carbohydrate meal. Within 1.5 hours of administration of insulin Lispro, blood glucose levels fall within the normal range of 70 to 120 milligrams per deciliter. In contrast, it takes 4 to 5 hours for blood glucose levels to fall back to normal after administration of recombinant human insulin.
That small switch at the end of the B chain enables rapid formation of the monomer, which is in fact the form which interacts with the receptor, and very rapid, efficient, effective triggering of the pharmacological response that we want. And in fact, it enables rapid clearance too. So you get the effect, and then it goes away. That's the hallmark of a good control element, right? When you flip the switch, you get the change you want. When you don't want it, the change you want goes away. And so that's why it was very good with postprandial meal-related glucose control.
Insulin Lispro shows how changing a protein's primary structure can drastically change the effectiveness of a biologic drug. Although the function of insulin Lispro is the same as endogenous insulin, inverting 2 amino acids weakens key interactions between the 2 monomers. It results in much less dimerization, makes the monomer more quickly available, and leads to better glucose control in diabetic patients. Other fast-acting insulins also contain substitutions at the C-terminal end of the B chain. These include aspart, which has a single amino acid substitution of proline to aspartic acid at B28, and glulisine, which has an amino acid substitution of lysine to glutamic acid at B29 and lysine for an asparagine at B3. But developing fast-acting insulins was not the only priority. Recall that a basal level of insulin is required to maintain healthy blood sugar levels. Since a diabetic cannot produce adequate insulin, an additional unmet medical need was long-acting insulin. One long-acting insulin that was developed using recombinant DNA technology is glargine. This insulin has amino acid substitutions that make it less soluble at physiological pH. Upon injection, the drug precipitates and then slowly solubilizes over time. Another very different approach, used in insulin detamere, involves adding a long-chain fatty acid to the B29 lysine. This post-translational modification encourages non-covalent and reversible absorption to serum albumin and prolongs its action. In the next segment, we'll look at monoclonal antibodies, another protein therapeutic where post-translational modifications and other structural elements have important ramifications for function.